Ambassador Roden, ladies and gentlemen, welcome everyone to the Australian National University. I'm delighted to see particularly so many of our new first year students here this afternoon. For those I haven't met, my name is Ian Young and I've got the very great honour to be Vice-Chancellor of this university. We're all incredibly privileged to be here this afternoon. It's not every day that you get the opportunity to speak to one Nobel Prize winner, but to have two of them here today is a real treat. Professor Dan Shechtman, who won the 2011 Nobel Prize for Chemistry, and Professor Brian Schmidt, who won the Nobel Prize for Physics that same year, have both kindly agreed to take time to sit down and give us some of their insights into what motivates and inspires them and what the path was like to winning a Nobel Prize. This event would most certainly not have been possible without the generous support of the Israeli Embassy, and I'd like to particularly thank Ambassador Roden and his staff for their assistance in making this afternoon possible. I also encourage all of our audience to ask questions, and particularly our students. This is a great opportunity, and so it's certainly not an opportunity which you should miss, and no time to be shy. I'd also, in a few moments, I'll hand over to Emma MacDonald, who will be moderating the discussion between Brian and Dan. Emma is the education reporter with the Canberra Times, and I'd particularly like to thank Emma for giving her time to moderate the discussion this afternoon. So without further ado, ladies and gentlemen, Emma MacDonald.
Thank you. So I have to say, as far as our week events are concerned, this is a bit of a highlight. I think it certainly beats a scavenger hunt, sausage sizzle, or even a tomato throwing competition, which I believe we've all missed in order to be here now. In my nearly 20-year journalism career, I've met 4 Nobel laureates, and each of them was an incredible privilege to meet. So for those of you who've assembled here today, to have 2 of them here in front of you, willing and able to answer your questions, well, I hope you just realise that this is rather incredible access. It may not happen again in your lifetime, and you need to think of some really tricky things to ask them, because quite frankly, between the 2 of them, they've already answered some of the universe's most pressing problems. I thought I'd get the ball rolling by introducing our scientific royalty and having them explain just a little bit about how they won the Nobel Prize. Professor Shechtman, can you explain your area of expertise and the work that led you to discover quasi-crystals, and what exactly is a quasi-crystal?
Okay. My area of expertise is crystallography. This is a science in which we study how atoms are arranged in a solid matter, and in particular in crystals. Crystals are materials in which the atoms are ordered. The field of my science, or the origin of my science, is in the year 1912. This is 101 years ago, with an experiment that provided us the tool to perform X-ray diffraction. And X-ray diffraction is a science in which you hit a solid material, or whatever you want, with a beam of X-rays, and out comes a diffraction pattern that enables us to analyze what is the structure of atoms within that crystal. For 70 years, from 1912 until 1982, all crystals that have been studied had something in common. They were ordered. Atoms were ordered in them, like tiles on the floor, but in 3 dimensions. And they were also periodic. There was a periodicity, same distance between each 2 atoms in any direction that you go. And I have discovered in 1982 a new class of crystals, which are ordered, and therefore crystals, but they are not periodic, they are quasi-periodic. Now, quasi-periodicity stems from an equation, the name stands for quasi-periodic equations in mathematics. We shall not go into that. But if you want to visualize what quasi-periodicity is, let me mention to you, number 1, Mr. Fibonacci. Anybody who knows about Fibonacci rabbits can know what is quasi-periodicity in 1 dimension along a line. 2 dimensions, may I mention Penrose, Roger Penrose and Penrose tiles. stars are quasi-periodic tiles in 2 dimensions. And in 3 dimensions are the crystals that I have discovered, in which the atomic order is ordered indeed, but not periodic. So that's about background for my discovery.
Now, Professor Schmidt may well be familiar to some of you. He is an astronomer at the Research School of Astronomy and Astrophysics here at the ANU, very proudly embraced by Canberra and the ANU. So you won the 2011 Nobel Prize for Physics for discovering that the universe is expanding rather than contracting, although
accelerating.
I've probably oversimplified that, and it's probably best you explain it.
So I came to Canberra at the end of 1994. And for my PhD, which I did at Harvard, I was out measuring how fast the universe was expanding. So when we go out and we look at galaxies, every galaxy, almost every galaxy in the universe is moving away from our own galaxy, the Milky Way. And the Milky Way is a collection of 100 billion stars, like the sun, which we live in, big spiral, big pinwheel. Now, it turns out that if you measure how far away a galaxy is, and you measure how fast it's moving from us, I can move that into reverse and figure out when that galaxy and our own galaxy were on top of each other. That's the time of the Big Bang. So when I measured that in 1993 for my PhD, I found out that the universe was about 14 billion years old, which was good because that was older than the stars in the universe, which had been a problem before, where it was younger, and that didn't really make a lot of sense. But I had to make an assumption. I had to make an assumption that the line was straight, that it wasn't changing speed over time. Yet we knew from Einstein's theory of gravity that gravity should slow the expansion of the universe, not dissimilar to how Earth's gravity slows a ball that I throw up in the air. So when I came to Australia, I said, I have a chance to do something big. I am going to measure how that rate of expansion changes back in time. And I can do that because if I look far enough away, light takes billions of years to reach us. And so I'm not seeing things as they are today. I'm seeing it as how it was billions of years ago. And so starting in 1995, when I arrived here, I started a program to look at exploding stars we call supernovae back in time. And we were able, with the technology of the day, for the first time, to look back about 6 billion years. And so we compared how fast the universe was expanding then to now, and when we did that comparison, we found that it was expanding slower in the past and had actually sped up over the last 6 billion years. Now that was the wrong answer. It was supposed to be slowing down. So in terms of weighing the universe, what we weighed was that the universe had negative mass, or that for whatever reason gravity was pushing rather than pulling. And it turns out this is because we believe now that the universe is 73% stuff we call dark energy, which is energy that is part of the fabric of space itself. And according to Einstein's equations, that makes gravity push rather than pull. So that was my discovery in 1998. And I'm going to add one little thing, just a piece of history to Danny's, is the big discovery in 1912 of X-ray diffraction was done by Bragg, who was Australia's previous last Nobel Prize winner in physics.
Yeah, let me add to that Bragg did not discover X-ray diffraction. It was rather Laureate who did the experiment. But the Bragg father and son developed the equation. And so this is why we should celebrate this year the year of crystallography, but we postponed it to next year because the budget is limited this year.
Yes. Very good.
Can I ask, just because everybody wants to know this, can I ask you, when you first got that phone call from Stockholm telling you that you'd won, prizable prizes, what was your very first initial gut reaction?
Okay. I have the prize in chemistry and Brian has the prize in physics, so he received the news one day before me. It was October 4 for you?
Yep, October 4 here in Australia.
In Australia. It was October 5 there in Israel, and in chemistry. And the way it worked was the following. I did not expect ever to receive the Nobel Prize in chemistry, although people told me that I am a candidate in physics, and the day of the announcement in physics gone by, I heard that you received the Nobel Prize in Physics, and I said, okay, fine, let the other prizes come first, and then one day maybe I will receive the Nobel Prize in Physics. I never knew when the Nobel Prize in Chemistry is announced. So, October 5, I sit at my desk in my office and I do what I do every day. You know, work on the computer. And then there is a telephone call. At the time in Israel is 15 minutes past 11 in the morning. So I pick up the phone, Danny speaking. Hello? This is the Royal Swedish Academy of Sciences. Please hold the line, a very important message. And I said, uh-oh. And then the head of the Committee of Chemistry talks to me and said, you won the Nobel Prize in Chemistry, I'm happy to tell you. And then other dignitaries speak to me, and the last person is somebody I know from the Royal Swedish Academy of Sciences, and they always use somebody that the laureate knows, because in the United States, when they wake them up at 3 o'clock in the morning, and you say, good morning, you have the Nobel Prize, damn you. So they have somebody whom they know that says, Jerry, wake up slowly, it's okay, it's okay. It's Andre from Stockholm, wake up. So this is why they have that. So I heard it, I talked to these people, and then I asked who else is with me. And they said, you're Lord, you're the discoverer. Okay. Don't tell anybody for half an hour, because at 15 minutes to 12, they announce it to the world. Hang up the phone, and I'm not telling anybody. Left my work, and I'm sitting there at my desk, gazing at the floor in front of me, thinking, what's going to happen now? What does it mean? What will follow? And I dreamed about different things that will happen, and I was so far from reality. I mean, I had very limited imagination of what's going to happen. And then 20 minutes later, I called Tzipi. Tzipi is my wife sitting right here. She's a professor in Haifa University. I called her on the phone and said, do you have students with me? With you? She said, yes, I have. I said, okay. I want to tell you that I won the Nobel Prize in Chemistry. Don't tell anybody for 10 minutes. She tells the students to go away, rushes to the computer center to see the announcement that they announced in Stockholm, and then she took a taxi to come to the Technion. We are in two different universities. Why taxi? Because my car didn't start this morning, I took her car. So, and so she came, but by the time she came, there was a stream of people rushing to my office, and I assume that's the same thing with you, Brian, that coming and cheering and yelling and photographers and ooh, and so this was these were the first minutes, the first half an hour. If you want later, I can continue.
So not dissimilar in my case. In my case, it was, the phone call came at 8:39 p.m. I was helping my wife cook dinner. I was doing a Thai green curry for anyone who's interested. And the phone call came, and the phone call said, my wife took the phone call and said, it's for you, kind of puzzled. And the woman said in a very good Swedish accent, is this Brian Schmidt? This is a very important phone call. And I said, yes, it's Brian Schmidt. And then she said, are you sure this is Brian Schmidt? And my suspicions were aroused in a different way than you might think, because earlier in the day, one of my graduate students handed me his wedding invitation for the 10th of December. You'll understand the importance of that date, Danny. And he said, when they call you tonight, tell them you're busy. And that's all he said. And I said, what are you talking about? So I hadn't really figured out that today was the announcement of the Physics Nobel Prize. So while people had talked about the potential of us winning the Nobel Prize, I will be honest, I personally did not take it that seriously. And so what I thought was unfolding was that my graduate student had gotten one of the Swedish students who were attending ANU to pull a prank on me. So I said, yes, of course, this is Brian Schmidt. And she said, well, okay, just a second. And said, this is from Sweden, and here is in my case, it was the chair of the physics group. and sort of sunk in that it was real very quickly then. And in my case, they didn't tell me not to announce it to anyone. They said, "We're going live now in 3 minutes. Would you just hang on so that you can go live with us?" And so I went and got my son, and we set up the laptop so we could watch it because it's streamed live on the web. And then the other question they asked me was, "And do you know Saul Perlmutter's phone number? Because we can't get a hold of him." And a few days earlier, they had had a rather unfortunate incident where one of the laureates had died in the few days between when they decided and when they announced. And so the first question that the press asked in their very elegant way was, "Are you sure all the laureates are alive?" That was the first question asked by the press gallery this year. So I did assure them that I had talked to Saul 2 days ago, as best we did.
Well, I got the phone call at about 9:30 and I was eating a chickpea curry, but I'm sure you don't want to hear any of my story. So Nobel Prizes are awarded for monumental, mould-breaking discoveries that turn conventional scientific theories on their head, and that's definitely the case with both of you. I'd like to ask Professor Shechtman, your discovery was rejected by the scientific community at first, and I've read that another Nobel Prize winner actually described you as a quasi-scientist. I'd like to know how that made you feel and how you maintained confident that your discovery was correct.
Okay. What's common to Brian and me is that they are both experimentalists. Experimentalists have a great advantage because we are professionals and we know our science, and when we observe something and examine it time and again, we know that we are right. This is opposed to theoreticians who develop theories or who believes in things that are correct or not correct. We have hard evidence. So in my case, I had hard evidence that my discovery is there, and and I repeated these experiments time and again, and I knew exactly what it was, and I knew exactly what it was not. And indeed, when I started to talk about the discovery, and I did talk to anybody who was willing to listen, I was in the United States doing my first sabbatical at NBS, National Bureau of Standards at the time. And the reactions some were between mild encouragement. For instance, my host, Professor John Kahn, said to me, "Danny, your observations are telling us something, and I challenge you to explain what it is," because it took some time to explain what it was. On the negative side, my group leader came one day to my office, smiling sheepishly and putting a book of X-ray crystallography on my desk, saying, "Danny, please read this book so you would understand that what you are talking about cannot be." And I said, I know this book, I teach at the Technion, I don't need to read it, I'm telling you my material is not in the book. A couple of days later, he threw me away from his group. He asked me to leave. He said, "You are a disgrace to my group. I don't want to be associated with you." And that was it. It was not as traumatic as it sounds now, because all I had to do is change group, and instead of reporting to his secretary, I reported to their secretary. I didn't have to leave my office, or I didn't have to leave my laboratory. So it was not so traumatic as it sounds now. But the feeling was sort of heavy and negative. 1984, myself and my colleagues, we published the first 2 papers that announced it, and from there on, we were a growing community of avant-garde, advanced, young scientists, physicists, chemists, mathematicians, material scientists who took my discovery and developed it into a field that grew very fast. Rejection did not cease, and there were 2 types of rejection. One, you may say, was legitimate. And what it was is the following. The International Union of Crystallography, this is the body that governs the science of crystallography, believed in X-ray diffraction, and they did not believe in electron diffraction, the tool that I have been using for the discovery. This is because electron diffraction at the time was not precise, but electron diffraction had a very good property. You can study very, very small crystals and see their rotational symmetry. And if you take an X-ray diffraction pattern for many crystals, you lose the rotational symmetry. And this is why the discoveries could have been made only by electron microscopy. They said, bring us X-ray diffraction, and then we can talk. It took us, the community, to grow large enough crystals. Large enough crystals meaning like a grain of sand. A portion of a millimeter is good enough. But we didn't have that. Our crystals were microns inside. After 3 years, 1987, we had the first result. Not me, my colleagues from France and from Japan sent me their X-ray diffraction pattern, Laureate pattern. I took them here to Australia, to Perth, where we had the International Union of Crystallographers meeting of 1987. I presented these results, and then the community said, now you're talking. Now it's okay. They established a committee that changed the definition of a crystal. This was a paradigm shift in our understanding of crystallography. Rejection did not cease, because then there was a most eminent scientist named Linus Pauling. Professor Linus Pauling was the godfather of the American Chemical Society. He was the most eminent chemist of the 20th century, certainly in the United States, but also maybe around the world. And he said what you just said. He said, on stages, this is 10% of the number of people that he had when he gave talks. Danny Shechtman is talking nonsense. There are no quasi-crystals, just quasi-scientists. And here is what is the real model. And he pulls behind a podium a model made of atoms, made of balls connected with sticks. And if you twin it here and here and here, then you'll get the diffraction pattern that Shechtman talked about. There is no need for quasi-periodicity. Periodicity is good enough. And when people told him after a few days, we checked your model, it doesn't work, it's a mistake, then he said, okay, then we have a larger model, and a larger model, larger model. To illustrate to you what it means is the following. Quasi-periodic materials require using of irrational numbers. For instance, the number pi, or the Fibonacci number tau, which is 1.618 and endless number of digits behind it. And if you try to approximate an irrational number by a fraction of two numbers divided by each other, then you can come as close as you want, but you will never be there. And this is what he did. He added digits to the rational number to approximate the irrational number, but you can never get there. So this was his fundamental basic mistake. The arguments went on and on and on, and it was not between me and him, it was between him and the American Chemical Society and everybody else that followed him, and the growing community of quasi-periodic material scientists who made the field grow more and more and more, and by the time that the controversy ended, it was 1994. So there were 10 years of very vicious controversy, and it ended only when he died in 1994.
Professor Schmidt, you didn't have to go through quite the same situation, but did you have to think long and hard before you announced to the world that the universe was in fact accelerating?
Yeah, so at the end of 1997, when we started seeing this, I have to admit, I first thought it must just be a mistake. So it was only through very careful checking of the work. It's very complicated. It wasn't, Danny's, if you ever see Danny give a scientific talk on this, it was literally, he looked into his microscope and he instantly knew what had happened. In our case, we had a lot of stuff we had to put together, but we went through it very carefully, and in the end, it was still there. And so I remember thinking, that's the end of my career in astronomy, because this is just too crazy, and people are going to rightfully assume I've made a mistake. I have to tell them, because that's what science is about. Science isn't about proving what you already know, it's about trying to learn new things, and sometimes the things that people assume are wrong. And so in our case, we did put our paper out, and the community was full of experimentalists like myself, who tend to be very conservative, and theorists, who actually tend to be a little more wild. And the theorists realized that this discovery fixed all of the current outstanding problems in cosmology with one stroke of the pen. So for them, it was like, thank you, right answer. All the experimentalists from my side said, this is too crazy. Those theorists have led you down the garden path. This cannot possibly be right. But they did have an open mind, and experiments followed, and then so we made our discovery at the beginning of 1998, and I would say, I think by May 2000, a defining experiment happened that really turned the tide, where everyone said, oh geez, our measurement must be right. We had improved our data a lot, but then there were other ways of looking at how the universe is constructed, and they were getting the same answer. Not quite as direct as what we got, but in a way which made it essentially impossible for us to be wrong without having made a catastrophic mistake.
Well, that was my next question. Have you ever considered the fact that some new up-and-comer, perhaps some new ANU researcher, may come along in future years and prove that your research was incomplete or incorrect?
Well, I certainly hope it's incomplete and someone figures that out, because we know that this idea of dark energy is incomplete, because we don't know what the dark energy is. I can say it's energy that's part of the fabric of space, but I have no idea why it's there. So, you know, I can make up something. And indeed, to explain the universe we live in, we have to make up 95.5% of the universe. 4.5% of the universe are atoms that we're made out of, and we know and we can see. 22% is dark matter, stuff that has gravity like atoms, but seemingly just travels right through the Earth, and we cannot see it because it never interacts with itself or with the atoms. And then 73% seems to be this stuff that has gravity that works in reverse and is part of the fabric of space itself. So one might ask, if we have to make up 95.5% of the universe to explain things, maybe we don't know what we're doing, and that would be a reasonable assertion. But the reality is that this model is able to make predictions. And the predictions it makes are quite complicated. And in every single case we've gone out, we have measured what was predicted in advance. And these are very complicated graphs and things that we can reproduce. And like it or not, reality is about being able to predict, to take new information and predict new things. That's what reality is. And that's why I say Newton's laws are not wrong, they were just incomplete. So yes, I think we're at that point now where we're unlikely to be wrong, but I certainly hope we're incomplete.
Well, in my case, and this holds true also for Brian, and I will put it in other words. I am a professional in my field. I'm an expert in my field, and I'm a good experimentalist, and I know my experiments well, from the stage in which I prepare my specimens to the stage in which I come up with the results. I do the whole thing. And therefore, because I am a professional, I trust my science. And there was nobody who came to me and said, I did the same electron microscopy, and here are the results that prove you wrong. This never happened, and it will never happen. Because everybody that repeated my experiments got the same results. They have received the same results. In fact, in the first week after the first announcement, I started to receive telephone calls from around the world. Danny, this is fantastic. We have it. People repeated my experiments. It's easy to do. You don't need equipment like your expensive equipment. Everybody has an electron microscope. They can prepare a specimen, repeat my experiment, and there you are. So the support came from all over the world right away. The people that objected me, and really it was Linus Pauling as a leader. There were other people that objected it, but not on principles. They said, for 70 years we studied crystals. We studied hundreds of thousands of different crystals, and nobody saw anything but periodic crystals. Why do you think that you found something else? Well, there it is. You know, sometimes it takes 70 years to find something which is unique and different. But the objection was not based on real science. It was based on empty words, although some of them came out from a very prominent scientist.
Today we've got a lot of students here about to start the long, hard slog of an undergraduate degree, and I wonder whether you could both cast your minds back to your very own week, your first week at university. What were your expectations and how did they differ to reality?
Okay, you know, when I was young as 10 years old or so, I was reading many books, and one of the books that I read that I loved very much was a book by Jules Verne named The Wondrous Island. I think this is a translation to English. He wrote it in French. And in that book, there's a group of 5 people stranded on an island, and the island is fine, but there's nobody there, and they create civilization, and they create all the tools. They make all the tools that they need to live modern life of the last century. And the main figure there was an engineer. He could do everything. He could do anything. And I wanted to be like him. I wanted to be an engineer from a very early age. So in Israel, when I grew up, I finished my high school studies and then went to the military service. At the time it was 2.5 years. Now it is 3 years for boys. And after that I registered to the Technion, which is a technical university in Haifa. We teach engineering and science there. And they accepted me, and I started to study mechanical engineering. My dream came true 4 years later, and in 1966 I became a mechanical engineer. Wonderful. Now my dream came true. I'm going to find a good job. And in 1966 there was a recession in Israel, and I could not find a job. There was no job available for us. So I said, well, maybe I'll do my master's degree, and in 2 years, after 2 years, I'll find a job. And indeed, after 2 years, I did find my job, but in the meantime, in these 2 years, I fell in love with science. And that sealed my fate, more or less. So this is how I got into science. And continued for my PhD, and the rest is history.
So for me, I grew up in the northern part of the United States in Alaska, so quite a remote place. And I was trying to figure out what I wanted to do. And I didn't know what I was going to do, so I decided to do astronomy, because I liked astronomy, but it seemed very impractical. So I went off to the University of Arizona, and that would have been September 1985 when I would have had my first week there. And the University of Arizona is a huge university that was fairly well known as being what they call a party school in the United States. And I hadn't quite understood what a party school was until I got there, and it's not quite like the ANU, and you should all be grateful. It was kind of crazy. And for me, I just took the opportunity to learn and do what a university is really good at, take a big variety of classes. I took a lot more classes than I had to. I sat in classes that I wasn't even taking just because I was interested in them. Seems kind of crazy, but...
Do you recommend students do that?
Yeah, why not? Because sometimes it's good just to... You've got some amazing lecturers here, and if you just show up in the class, just tell them what you're doing. So I just want to listen to you lecture. Trust me, they love you when you say that. And especially you don't have to grade the homework, you don't have to deal with any issues. It's great. So I did that. And I did that because that's what, to me, university was about. It was about learning and enjoying myself. And I did all that, and I still had huge amounts of free time. So I started on my path of doing astronomy without any expectation of ever being an astronomer. I knew only a few thousand people in the world were astronomers, and it certainly didn't seem to me like I was going to be one of those. I grew up in the middle of nowhere in a kind of normal high school, and I didn't seem particularly special. And so it wasn't until, at the end of 4 years of university that I applied to graduate school, and I got into almost every place that I applied, and I was kind of stunned. I was like, well, I was the first student to have done that in like 10 or 15 years at the university. So I was kind of surprised, but I think that means the lesson you can take is have fun, enjoy yourself, and don't box your future in. I think you can see Danny didn't box his future in, and I certainly didn't either. I was really very surprised with what I was able to achieve, and that was just getting into graduate school.
Do you have any regrets?
Do I have any regrets?
Just about
I'm supposed to say yes, but the answer is, I don't know. I've always sort of done what I thought best at the time. I've always had a pretty good work-life balance. So, no, I don't have anything that just jumps out at me that I have regrets. I just sort of live life, try to make life not be very complicated. And it's worked for me.
I might see whether anyone in the audience has any questions. I've got plenty I can keep going, but does anyone have a burning issue they'd like either scientist to address? Anyone?
No, they're just like normal undergraduates.
Go for it.
There's going to be a microphone.
Hi, I'm Tim. I'm starting my first year this year, looking at theoretical physics as one of my majors. But my question is sort of around university funding and tertiary funding from the federal government. And I was wondering what your opinion is on future funding with another election being called, because I know there's been previous cuts to tertiary funding before, and I was wondering what your opinion is on the issue.
Okay, well,
let me suggest something.
Yeah.
Can you repeat the question to everybody? Because
cool.
I can. He asked. Sorry, yeah, you heard that one. He asked what you both thought about federal government cuts to higher education. I'm not sure what the case is in Israel, but the pickings are pretty slim here in Australia.
So I think that, and I think Danny can give a reflection on what's like in another country. So the universities are huge entities, and the ability to do things is pretty much unlimited. We're really about exploring, and there's huge areas to do it. So universities have, in some sense, been given a fair bit more money over the last several years. But they've also been asked to do funny things, like teach many, many more students, and the money is coming in ways which, as an economist, which my wife is, would say is distortionary. It's causing universities have to cross-subsidize and do things that makes life painful for everyone. And so that's one of the things we need to address. If we do wholesale cuts to the university, you bet it's going to be terrible, and that's not what this country needs right now. But I think the federal government thinking about how it funds the university sector and says, for example, do any of the universities get rewarded right now for teaching you guys well? Nope, we don't. Turns out we don't at all. That's not a metric that we get funded by. And yet that's something they want us to do well. We do get rewarded for doing research well, but through a very funny process. And so I think my goal would be to keep funding sort of at the level, but to make the funding much easier to spend sensibly, and that would be a really good outcome for us over the next couple of years. So yeah, we're always worried about cuts. It's a tight budget, and we need you to scream if they cut hard, but a little bit of change wouldn't be bad for the sector either.
the question was about funding for research or funding for universities in general?
Universities in general, but also research.
Okay. The future of every country, and certainly that of Australia, depends on the quality of education. This is your future. You are the future of Australia. And the better the education that you receive, the better it is for Australia. And politicians that do not understand that should be replaced. So this is fundamental. This is fundamental. Universities should be well funded at all times, and especially such subjects that have added value to the future of the country, such as the economical future of the country, that means engineering and sciences and so on. So, because this is the future, and because the investment is a long range, you don't see the results within 3-4 years, and politicians tend to say, well, that's a problem of the next government, and it may not be us, then why bother with that? We want immediate results so that we will be voted in against. But really, education is job one for every country and for every government. And education means not only universities, it starts in the kindergarten, through primary school, secondary school, universities and high degrees in universities. And all of it should be very well supported. That means getting the best teachers, that means getting the best programs, meaning building a powerful array of education system. So this is really, in my opinion, job one of every government.
But you would agree that we do need to spend it strategically. It's not spend the money strategically. It's not just throwing money. We can do it well, and I agree with everything you say. But it's not a matter of just throwing money at it. It's a matter of thinking about how we spend it.
In his State of the Union, President Obama this week talked up the importance of scientific endeavour, and he said, now is the time to reach a level of research and development not seen since the height of the space race. Now, I may be just a little bit cynical. Do you think this is anything more than political rhetoric? Do you think he'll back it up?
You want me to speak for Obama?
Someone has to.
I think Obama can do anything he wants, but I think the House, which initiates bills of finance in the United States, is likely to be fairly tight on the purse strings.
Up to now, Obama showed that he really tries to do what he talks about. He has a good record of at least trying to do it. It's not easy to pass resolutions through the American system, but especially when there are a minority somewhere. But he really tries. So I believe that he will do that. He will try to do that at least.
Try.
Yep.
If you were both Prime Minister for the day and you could be granted one policy implemented immediately, one budget wish, what do you think you'd ask for?
Education.
Me too.
No question about it. Education. But do it wisely. Do it wisely. It doesn't mean spreading the money and telling the system, do what you need. No. Make sure that you have the best teachers. That means make sure that you have the best schools that make teachers of all levels. That means having the best headmasters for the different schools, from primary school to Vice-Chancellors and so on. And making sure that controlling the system in such a way, not to the details, not the micromanagement, but in general, tell the system, this is important, this is important, this is important, and here is where we put our money. We need better teachers, at all times, always, better teachers, better programs, and so that you will prepare better students for a very early stage. Very early stage. I can tell you that I now started a program in Israel to teach science to kindergarten children, age 5, real science, real physics, physics, no equations, but real physics. I want them to like science from a very early age.
What about you?
Yeah, so my answer is almost identical, and indeed, I think I've been quoted in saying this, the same question, which is funding, and I'm going to be more specific, education, very important, but I would say getting higher qualified and teachers who are respected across the country, and I have personally supported a program called Primary Connections, which is a way of getting K through 6, the teachers schooled up in teaching science across the thing. So I think you and I are in violent agreement.
There was someone just here with it? Yes? Oh, just wait for the microphone.
My name is Peter. I'm a redic student at Crawford. Just a comment first of all. I think for the organizers it's unfair to give us 2 eminent persons. Two eminent persons on the one afternoon. There's a lot that we can extract from either one of them, and so that's, I think, a bit unfair.
You still get me.
Thank you.
I do things at the conference.
Thank you.
That's good.
Good one. My question is in relation to obviously what you've gathered from your research will add to the body of knowledge within physics and chemistry. My question is, how do you relate your findings to ordinary human existence?
Okay.
Well, in my case, I find astronomy being one of the most fundamental, and cosmology being one of the most fundamental things that humanity has. I have been, wandering around to 8-year-olds in the Australian outback, and if you talk about the stars, they ask questions. And those questions are the same questions my friends had when I grew up in Alaska in the United States, and the same questions that the kids I met in Namibia had. It's very universal. What is our place in the universe? And the reason we do that is it allows you to ask bigger questions of how does physics work at a very fundamental level. And that turns out to be very useful. It's a way of discovering and understanding the laws of nature. And these have a way to get people and kids who are 10 years old or 8 years old interested in science. But it's also a way of inventing things. And so many of my students do not work as astronomers anymore. They work in various areas, learning their ways of thinking and the techniques that they develop to do new things that people see as being directly useful on a couple-year time scale. The most obvious one is one of our colleagues invented Wi-Fi, which is used throughout the world. And instead of, he used the techniques he developed to look for evaporating black holes predicted by Stephen Hawking. Never found them, but he invented Wi-Fi, which, I think the evaporating black holes were just as interesting, but Wi-Fi, probably more people think's more valuable. The reality is the basic research we do leads to that. But I can't tell you what, my research is going to lead to. It may lead to nothing, but it may inspire some kid to go and do some major thing in the future. It's a very complex web of basic research, feeding the ideas up through society. You get rid of that, then in the short term, a couple years, you save money. But the ideas are gone, and you're not gonna, you can only then develop what you already know, and you'll find that society breaks down and can no longer innovate and develop new ideas.
So to respond to the question, how do we relate our science, which is quite complicated, to the general media and to students, right?
To humanity. How is your science relevant to humanity?
Okay. Okay, well, any discovery in science is relevant to humanity. Sometimes it's right away, like when you discover a new vaccine, for instance. Then in a couple of years you have saved many lives. Sometimes it's a long range, such as in Brian's discovery. And in my discovery, it's somewhere in between. It's a new set of materials which have interesting properties. And in order to use new materials, you need to understand these properties and find the properties which are unique and useful and can be applied. So you can have applications. In my case, I can tell you that some of the interesting property of quasi-periodic materials, and there are hundreds of them, many of them, are, for instance, low heat conductivity, heat insulators in a way. Very interesting electrical conductivity, interesting magnetic properties, interesting optical properties, very interesting hardness. Surface properties are interesting. These are non-stick materials and so on. And several products have been developed based on these interesting materials. But let me tell you a little story so that you'll explain how things work. 40 years ago, I did my postdoc. And in my postdoc, I did a study on materials that are called titanium aluminides. It's a combination of titanium and aluminum. And titanium aluminides were thought to be very useful to be used at high temperatures, such as in jet engines. And the jet engine companies, such as General Electric and other jet engine companies, were very interested in that. And I was the one who published the first papers who explained the deformation mechanism at different temperatures in these materials. And we worked on their development. 3 years later, I finished my postdoc, and they offered me a position in Israel, and I left the field. 2 months ago, 40 years later, I received an email from the head of the program. He said, "Danny, we have titanium aluminides in jet engines." It took 40 years of huge investments by powerful companies and the US Air Force to bring these materials into jet engines. And when I studied them, I thought that it will be 1 year and they will be there. They were so good. So sometimes to introduce new materials takes a long time, but eventually it works.
Does anyone have one final last question? Yep. If you've got a loud voice, you could try yelling.
I'm a science student, and I was wondering, do you think there are any attributes that sets Nobel laureates apart from all other scientists?
Good question. He asked whether there were any attributes that would set a Nobel laureate away apart from an average scientist.
Okay. let me tell you, there are two types of Nobel laureates in science. I'm not talking about Nobel laureates in peace. I know nothing about that. But in science, most of the Nobel laureates are experimentalists, such as the one sitting here, but very many of us are experimentalists. Very few are theoreticians. Einstein, the greatest of them all, theoretician. Now, so the question really is, what is the difference between us and other people? I don't think that there is a fundamental difference, but then there is an accumulation of properties, of features. For instance, first of all, we have to be professionals. We have to know very well our science. You have to be an expert, but then there are many experts. Another thing is that you have to have a good eye for observation, to see that something is different. Number three, once you realize that something is different, then grab onto it and don't let go. Even though some people say that you are a quasi-scientist, if you trust yourself, and if you can trust yourself if you're an expert, then don't let go. And so this is another one. And the combination of that and patience and precision work and repeating your experiments, all that brings about the prize eventually. However, luck plays a great role in that. If Brian would have chosen another subject, he would be a great scientist, but not a Nobel. If I wouldn't observe quasi-periodic materials, I would be a great scientist. I wouldn't get the Nobel Prize. Luck plays a role in it, but you have to help luck.
Yes. So Danny has more or less said exactly what I would say, which is that you do need to be very good, technically able, capable. I think in a modern day it helps to be actually quite a good communicator, because one of the things that when you get a crazy result is you have to convince people you are right. And you should not think that that is easy. Science is very conservative, and it does not like things that overturn the current orthodoxy. And of course, you do need to, when luck strikes, you need to be able to run with it. And you need to be able to go through, convince people, but also do the follow-up work and remain relevant in the field. And one of the interesting things is Danny and I both went to Lindau this year. And one thing I did realize is that Nobel laureates, especially in physics, are somewhat eccentric. Now, I haven't yet figured out, since I don't think Danny is that eccentric, and I know I'm not eccentric.
My wife will not agree.
I haven't yet figured out if this is something that happens to you, or is the way you were born. And so I don't know, Danny, have you figured out, are we just
being
kind of the normal part of the Nobel laureate chain?
Being eccentric?
Yeah, I think we're less eccentric than the people I met at Lindau.
I can tell you one. I'm not sure that. Well, we are all eccentric in a way, but not crazy. I mean, it is a.
But you would have to say there were a couple people there, borderline.
Yeah, right. Yes, but I can tell you that
he's too diplomatic.
That there is a history in my life in which I was one against the world. From a very early age, I was arguing with colleagues and friends in my classroom and so on, and I knew that I was right, and the whole class said, "You are stupid, you don't understand anything," and so on and so forth. And I knew that I was right. Okay, fine, no problem. And I still remember cases in which, one after one, I had to argue with colleagues, and this was just another one. The discovery was just another one.
It's probably a good point to end the afternoon. I thank you both very, very much for giving us your time. I hope you all look very interested, and it's really wonderful to stare out at your faces. So good luck with the first year. Don't party too hard. Don't party too little. Balance. And go to a few classes that you have no intention of taking and just sit in and listen. Thank you very much.